Yay, recording in progress. Cool, welcome everyone. Today we are just gonna go over disjoint sets, hash tables, and heaps. For me, I will be, next slide. We'll be going through disjoint sets, and we have two other amazing tutors right here that will take you through hash tables and heaps. So, disjoint sets, let's go ahead. So for this class, disjoint sets is defined with two methods. We have the connect method, which basically determines or connects two nodes, X and Y. And then we also have a is connected method, which returns true if X and Y are within the same set. And another important method for you just to know, which isn't necessarily defined within the disjoint set interface, is the find method, which returns the root of a given item. So let's take a quick dive into the different implementations from the lecture. So we have our quick find. And the underlying structure that is used to implement quick find is an array structure. And as the name implies, quick find is great for finding items quickly because we only need to check if the values within each array are equal. And this has a runtime, a constant runtime for is connected and a linear runtime for connect. So let's take a quick look at the diagram. Again, we notice that within the underlying array structure, we have the value of the array indicating which set each item is actually in. Should be simple. Hopefully no questions about that. All right, and then we have our quick union. So this is again using a array, underlying array structure. And the primary difference is that whereas the quick find used the array value to determine which set the index is in, the quick union uses the parent index. And so to indicate whether or not a index is actually the root, we use -1. And just a quick note, every item is its own root in the beginning. So when we instantiate a quick union object, the underlying array should be all -1s. Yeah, so this is our lovely diagram that I stole from lecture. We would notice that within this subset, our root 0 has the array value of -1. And then we have a child of 0, 1, and then we notice that the array value in this case would be 0, which is the parent node. All right. So one of the issues with quick union actually is that we can get a really long spindly tree or just a long branch, and that would occur when we have connect 0 and 1, connect 1 and 2, connect 2 and 3, and so forth. So you can imagine just a long tree with essentially one root and a bunch of children with only one children. And that creates problems when it comes down to efficiency. And that is why we define weighted quick unions, which is very similar to quick unions with two primary differences. One is that we always add our smaller tree to our bigger tree. And then the next thing is that instead of using -1 to indicate that a index is the root, we use the negated value of the set, right? Because we want to quickly determine which tree is bigger or which tree is smaller such that we can add them correspondingly. So let's take a quick look at a diagram. So right here, if you can notice at index 0, we have -4, which indicates that index 0. Do we have a question? Maybe not. I guess not. So -4 indicates that 0 is a root because of the negated value. And we also know that that set has a size of 4. So let's do a quick example, connect 3 and 4. In this case, when we connect 3 and 4, we note that this tree is of size 4 and that the little tree here of 4 and 5 is size 2. And again, we always add the smaller tree to the bigger tree. And in this case, we would update our size from -4 to -6. And then we would also update the parent of 4, index 4, should now be 0. All right. Oh, there might have been a mistake on that slide. Okay. So weighted quick union with path compression is basically just a subset or a special case of weighted quick union. And essentially, whenever find is called, remember back when we defined that find is a method that returns the root of x. Oh, also I can't see the chat, so let's see.
No worries, Jesse, I got you.
Okay, my bad. So basically, whenever a find is called, we will move the node. We'll change the value of the node to the actual set's root. And so just quick diagram. So in this case, when we have this, the tree to the left is the one that has not been compressed. And if we were to call connect, or if we were to call find 15 on it, then we will travel up the tree. And as we travel up, we'll connect the 15 to the root of the set. So it would be like 15, oh, is root. The root of the set is 0. And then 11, 0, 5, 0, 1 is already connected to 0. Notice that 5 and 12 here, because 12 wasn't called, it remains under 5. Cool. So this is a quick graph of the runtime, and I would highly recommend you guys to sort of just jot this down in your cheat sheet because you never know when this will come up. All right, so let's get down to some practice. In this case, we want to determine whether or not this diagram is possible with a weighted quick union object. And in this case, we do not have path compression. So I'll give you guys about 30 seconds or so, then feel free to spam the chat. If you have any thoughts, definitely just go ahead and give it a shot. Okay, cool. It doesn't seem like anyone has any thoughts, but that's fine. So this is actually not possible. And remember, this would break the first rule of weighted quick union, where we cannot add a larger tree to a smaller tree, where the correct way would be always adding the smaller tree to the larger tree. So in this case, 2 would actually come out of 5 instead of coming out of 3. Okay, cool. Again, we have another quick, hopefully simple question for practice. I'll give you guys another like 30 seconds or so, jot it down on a piece of paper or something. All right, let's go ahead and continue here. So in this case, this diagram is actually possible with quick union. If we look at the given order of connect calls, we know that we would have connect 2 with 0, and then we connect 4 with 0. And then we can either connect 3 and 5. The key thing is that we need to connect 3 and 5 before we ever connect any of these to 0. So we'd connect 3 and 5 together, and then connect 0 and 6, and then eventually connect 3 and 5 together. And that is our answer.
Hey, Jesse.
Mhm.
There's a couple of questions about going over, I believe, again, the differences between the different sorts of quick union, and also perhaps why the last one was not possible. There seems to be
Okay.
some confusion.
Okay, yeah, for sure. So the different quick unions, let's go back. So the most basic quick union is just quick union. And basically, the two things is that the actual value within the array is the parent value, right? So when we're looking at node 1, the value within it, because it is not a root, is 0, which is the parent node. And then for weighted quick union, it's essentially the same thing with two conditions or two changes. One is that you always add the smaller tree to the bigger tree. And then the second change is that instead of using -1 to indicate that it is a root, we use the negated size to indicate that it is a root. And because we use the negative size, we can very easily obtain the size of each set. So those should be the two quick unions, or yes. And then we have quick union with path compression. So the point of path compression is basically just to make our program a little bit more efficient. So instead of having to traverse through the tree every single time in order to determine what the root is, we would simply, we would only need to traverse like one node. And so how path compression works is that as we traverse up the tree with find, it will change the value corresponding to the parent to the set's root. So in this case, if we were to call find 15, as we traverse up the tree, we will be changing the value of each node to 0. Hopefully that makes a little bit more sense. And as to why this is not possible, this is again weighted quick union. Remember that for us, if you were to ignore the fact that there's a 2 here, essentially we would be connecting 3 and 5. And for us to connect 2 to 3, we know that the 5-3 set is larger than a single set. Thus, 2 would have to go to 5 in order to satisfy the weighted quick union rules. Cool. All right. Feel free to interrupt me if you guys have any more questions.
I have a question really quick.
Mhm.
So back with compression, the only way that's different from weighted quick union is like if you make a call like to find a node, is that right? And then it changes the structure of the tree.
Correct. Also note that find can possibly be called within connect and also within is connected.
Okay, thank you.
Okay, cool. Right, this is not possible. And then this is possible with the following calls. All right, let's move on to one last exercise. So basically, we want a little bit of practice with disjoint sets and how that might be used within an actual program. So here, your Professor Oski has a terrible memory. So we'd love if you could write a program that helps him keep track of groups. We love group projects. It's a fun thing. In this project, you should assign a random lead. So this lead can be any arbitrary person within each group. And there's constraint of all the SIDs. There's 100 students in the class, and the SIDs are from 0 to 99. And basically, you can assume that these three methods here have already been correctly implemented and there are no other methods within this class. So go ahead and, oh, yes. So in the chat, Angeli said that the convention will be specified on the test, but usually it is to have the smaller root to be the parent. Is this in reference to the exercise?
Oh no, this is in reference to the fact that on homework 2, they specified the larger root will become the parent in a tie-breaking scenario. So people were confused by that, and that's what we're saying. In general, if we have some tests, we will tell you which one will become the root, but you can just say, as a general case, outside of this class, you'll have the smaller root usually be the parent in these situations.
Okay, got it. Thank you. Okay, cool. So yes, please go ahead and take a couple of minutes just to think about how you would write the constructor, and afterwards we'll go over the constructor before we sort of go through group lead. All right, if you guys are done, could you potentially react or put up a yes within the participants? All right, let's give it one more minute. All right, let's go ahead and see what we have. So, well, here's the answer, obviously. But the reasoning behind, I guess, the answer is that we are sort of trying to use a disjoint set and, or more specifically, a weighted quick union sort of structure where we instantiate a new array of length 100 because we know that we have 100 students, and we take a very similar approach using the negation to indicate the lead within each set, and also the I or the index will represent the student ID. So this should hopefully mirror the structure of a weighted quick union relatively closely. Let me know if you guys want a little bit more time to complete group lead. All right, if not, that's totally fine. Oh, yes, why do we set elements to -I? Why are we using, okay, so we aren't exactly using weighted quick union here. This is meant to sort of mirror the structure of weighted quick union, where we use our negation to indicate more data, and we also use the magnitude of whatever the value is to give us more data. So because we want to determine who the lead of a group is, and also we want to know the SID of that group, we use I to represent the SID of the group, and we also use a negation to indicate that it is the actual lead.
I was wondering, I thought it's supposed to be negative. The negative is also the size of that number.
Yes, that is correct for weighted quick union, but remember in this case, we are trying to create, let's go back. We're trying to create a program that helps keep track of not only groups, but also who the lead within a group is. So it's not quite a weighted quick union, but it takes the idea of using negated values and the magnitude of those negated values to give us more information about a set, or in this case, a group.
Okay.
Okay, let's see. How do we fill everything in the array ID with the negative index or -1? Oh, so yes, in this case, we are filling it with the negative SID or the negative index. The same thing here. All right, so without further ado, let's go on and take a look at group lead. There's many different ways to implement this, but this is just sort of my thoughts on it. So group lead should return a array list. So that means that we obviously need to instantiate a new array list. And since we know that the SIDs are primitive int objects, and that array list must take in a object, in this case, the wrapper class for an primitive int is the integer object. So we instantiate that. And then we can go ahead and loop through the array. And because we had previously defined the value within the array, if it's negative, we know that it is the lead of the group. And also we know that the actual value, the magnitude of that value would be the SID corresponding to who the lead of the group is. We'd simply go through the array and add in every index that is less than 0. So there's a specific case though that was a little bit tricky where in Java, you can't have a -0. And because we had SIDs from 0 to 99, we had to write a specific case to sort of handle that issue, right? So in this case, in our if statement, if our index I is of 0, and we also know that the value corresponding to the array at index 0 is also equal to 0, then that means that we are our own leader. So in that case, we should also add the SID of 0 to our leads array. All right, let's see. We have some questions in the chat. So were all the students just added into the list? No. We assume that our join function works so that when groups are created, we'll be joining the SIDs of different group members together. Let's see. Can you explain one more time why the I0 would be 0? Okay, yes. So remember, we have a special case where in Java, it is not possible to have a -0. So our first if condition, where the value within the index is less than 0, will never occur in the manner that if the 0th index is equal to 0. So if the first value at index 0 is equal to 0, we know that person 0 is sort of their own group lead.
To answer a question that I'm seeing repeatedly in the chat, this is more an implementation of a quick union rather than weighted quick union. And since we are not basically accounting for size when we combine groups in this class, instead of keeping the negative of the size, we are keeping the negative of the leader of each group as the value of like the root of the tree. So -99, for instance, would mean that the leader is 99, not that there's 99 items with 99 people within that group. I hope that clears that up.
Right, my apologies. The main takeaway that I want you guys to have is that the negative value can represent a lot of different things. So if you were to have, if you wanted to encode more data within a set, you can totally use the root's negative value to give you more information. Cool. Do we have any other questions? Can you explain the if statement or else if statement? So yeah, so the issue again is that Java cannot have a -0. So that means that there's one special case. The special case is that if person with the SID 0 is the leader of a group, right? That means that as we iterate through, the actual value of the person is never less than 0, right? Because the value within the array is actually 0. So in order to handle that case, we want to check if, first off, if the counter, if I is equal to 0, and then we also want to check if the actual value of within the array is equal to 0. That's like sort of the special case where, yes, perfect, awesome.
Yeah,
Cool.
just in case people weren't, I guess recording people can't see the chat. Like just to summarize real quick, it's because if you're looking at some random thing in the array, right? If you're like the 5th item has value 0, then that's referring to its parent being the 0th person, right? But 0 times -1 is still 0. So when you're on the 0th person, if their value is 0, that means that they are the leader. but it's not a negative number. So we have to have a special case for just the 0th person because of that weird issue of 0 times -1 being 0. But other than that, that's why we have the edge case. Everything else is normal.
Perfect, thank you. All right, and that pretty much ends my part of the presentation. Let's see.
Yes, awesome. I will be going over hash tables. So let me just present here. Is everyone able to see my screen okay? Cool. Okay. Yeah, so we'll be going over hash tables today. First, let's cover what hashing is. So before we jump into hash tables will essentially allow us to store, look up, and remove items in amortized constant time under certain assumptions. So we'll also be going over those assumptions as we go through this presentation. But the main process for adding into a hash table is that first you want a hash code, which will map a certain object to a code independent of your hash table. And this code is usually some kind of integer. You guys might have seen this in your Gitlet implementation where sometimes when you want to use like that SHA function, SHA-1 or whatever, you're hashing, right? And a reducing function, which is usually a modulus function, will map the code to a bin or bucket in a specific hash table. And so modulus will essentially like allow you to like if you have a huge number, you can reduce that to a smaller number, which will correspond to a specific bin in your hash table. And so just to talk about like a diagram for this, let's see, cool. So if you want to visualize the process, we start with our object on the left side, and then we use our .hashcode function to convert this object. This might be like a dog object that you guys saw in your lab, or like something else that's not represented as a number. So this hash code is just going to take this object and convert it to some enormous number. And then we're going to use our reducing function, which is typically like it's our modulus function. So this is going to spit out some number mod n, where n is the number of buckets you have in your hash table. And so once we do that, we now have a bucket in our hash table that we can map this object to. And so we can essentially put it into that bucket in our hash table. And so that's like the overall diagram for like this entire process. And now we can actually step through the more like the specifics of each step. So first, let's cover hash functions. We kind of talked about how you can take like this object and convert it into a number, right? But how does that work? So the necessary properties of any hash function are that number one, it has to be deterministic. And what does this mean? A deterministic function means that repeated calls to this function should return the same value if the object is the same. So for instance, if I had a specific dog, right? Like let's say, I don't know, like a poodle, and I were to get a hash code for that poodle. And let's say the hash code just returned like the number 2. This is not maybe a great hash function, but it's returning the number 2. If I were to take that same poodle and pass that through the same hash function, I should get the exact same number. I should not get like number 3, because that would mean that the poodle maps to 2 different numbers and you don't want that. The other thing that we can use to check whether 2 objects are equal is the dot equals method. I would really recommend using the dot equals method and not the 2 equals signs, because when you're using objects, the dot equals method can actually compare objects, while the double equals might return like an incorrect solution. You guys might have seen this as you were implementing stuff in your projects and in the lab. So if dot equals returns true, the hash function should also return the same thing for both. And so an instance, like an example of this is why the style checker got mad at you for overriding dot equals without overriding hash code in project 1, because we're using the dot equals method within our hash code. Awesome. And so the other thing we want to see in our hash function is that it's consistent. So this means that if A and B are both objects and A dot equals B, then the hash code of A should be the same as the hash code of B. And now you guys are probably wondering, well, you just told us you have to use dot equals. Why are you using the double equals here? That's because hash code is going to be an integer. And so any primitive type can actually be compared with a double equal. So yeah, that's what that bullet point basically says. Awesome. And so now to go a little bit more into depth on what makes a good hash function, right? Because we can have a hash function, but a hash function that's good is going to allow us to get a better runtime when we're using them for hash tables. Hash functions are separate from hash tables. Like you can have a hash function and not necessarily map that to a hash table. But for the purposes of 61B, we're usually going to be using hash functions to go into a hash table. And so a hash function is good if it's uniform. And so this means that the value of any hash key is randomly distributed across all integers. And so like if you were to, you essentially want to be able to get like a uniform distribution of keys across all the integers that you can choose from. And this also will result in fewer collisions. And a collision happens when two different objects map to the same hash code. And you really don't want that. And we'll go over why we don't want that, specifically in the case of hash tables later on. But yeah. And the second thing we want to look at is the efficiency. So a hash function is good if it's efficient. And this means that it takes constant time to compute the hash code. So we really want to try when we're making our hash functions to have it be a constant time function. Awesome. So now I mentioned collisions briefly in the previous slide. So here we're going to talk a little bit more about what makes a collision. Yeah, so a hash table collision, I wouldn't confuse that with a hash collision. So a hash collision is when you're using your hash function to assign like the integers, but a hash table collision is when you're actually taking that object that we talked about earlier and putting it into a hash table. So on the right here, we can actually see an example of a hash table. I took it from the lecture slide. So we can see that we have a bunch of buckets like 0 through 9, and we can see that within each bucket, like 0, for instance, has 3 objects within it. In this instance, we're like putting words in there in different languages. So it's like a collision happens when 2 objects map to the same bin. So for instance, in the 0th bucket, we have hug and then 2 other words in different languages that are both in that same bucket. And so all of these are basically mapped to the same bin. Collisions can cause linked lists within the bins to grow in externally changed hash tables. So in an externally chained hash table, we're essentially going to be able to keep adding on to one bucket. So as we can see here, it kind of looks like a linked list structure in that 0th bin. And that's because this hash table that we're using is externally chained. And we don't want a linked list, because if you guys remember from earlier, a linked list, in order to find any object within a linked list, that's going to take order of n time. But we actually want our hash tables you want lookup to be able to happen in constant time. And so that's why we really want to avoid collisions. And I see in the chat, someone had asked, how are hash table collisions and hash collisions different again? The concept of collision is the same for both. I wouldn't worry about it too much. I just wanted to make a point that hash collisions, like when we talk about collisions within hash functions, that's when, if we go back to the previous slide, actually, that's when we are distributing like a hash key across all integers. But a hash table collision ends up when, yeah, as Nikhil said, when 2 items end up in the same bucket in the hash table. Awesome. And so good hash functions will always result in fewer collisions because of the uniform distribution property that we talked about in the previous slide than a bad hash function, as they're unlikely to map multiple keys to the same bin. So we see here on the right that we have a lot of linked lists in this hash table. A better way to distribute these different words would be if each of them were in their own bucket, because then when we want to retrieve like a value from bucket 0, we could just get one value and we might not have to iterate through all of those objects in that bucket to get maybe like the last value in there. So that's why we want a function with fewer collisions. Awesome. So now we can talk about load factor. This is really important when determining like collisions within a hash table. So if we have n items in a hash table and we have m buckets, then the load factor is going to be n divided by m. So we can basically think about this as the average number of items per bin. If the load factor is less than some constant value that we will usually specify, like usually on like an exam, it'll tell you, oh, you want your load factor to remain under this value. We can have constant amortized access time. So what this means is that you can retrieve any object within constant time on average, assuming that the hash function has a good distribution. And so after our load factor reaches a certain threshold, which is like that constant value that is in the second bullet point, we should actually end up resizing our hash table to distribute keys more evenly. And so the way we do this is by increasing m, because you're dividing n over m. So if your like value, let's say, is greater than 1, then if you increase the denominator, it's going to end up being less than 1 again. And so you're going to have like not as many like objects mapped to buckets. You don't want to have as many collisions. And so yeah, we can resize our hash table to distribute the keys. And then the last thing is that we need to choose hash codes that distribute items evenly across the bins to guarantee good performance. And that's like kind of a point that I've been talking about repeatedly in the previous slides as well. That's kind of what makes hash maps so great. And that's what enables like that constant time. Like it really depends on your hash code and your hash function. So if you want to compare the runtime of a hash map or like a hash table with other data structures, we can look at how like it's actually pretty good, right? You would be able to retrieve, like use the contains method and the add method. Both of those are going to happen in constant time if you have a good hash function. While for other like data structures that we looked at, like binary search trees, like a data indexed array, a hash table that has no resizing. So that's like, if you have no resizing, that means it's going to allow collisions, and you're basically going to end up with that linked list structure that we were talking about earlier. Like those are all like worse than having a hash table that's externally chained and has resizing. And so that's why this is super important, to be able to resize and to be able to distribute your keys evenly across the buckets, because we really get that constant time speed that we're looking for. And yeah, just I would note that it includes amortized. Amortized means on average. You can't say that it's true for every single like instance. And then we're assuming that the items are evenly spread across the buckets. And so that's where the hash function comes into play. Awesome. So we're going to do a quick check on hashing. So there's a couple of questions on the slide that I want you guys to like take like maybe a minute or so to think about. And then afterwards, I'll ask you guys what your thoughts are. So the first question is, if two items have the same hash code, will they be in the same bucket? The second question, I'm just going to give them all to you right now, and so you guys can think about them all. If there are multiple items in the same bucket, how would we retrieve one of them from an externally chained hash table? And the third one is, suppose you have a good hash function that assigns words to bins based on the ASCII value of the first letter of the word. Is this a good hash function? Why or why not? So there's like 3 questions here. I'm going to give you guys maybe like 2 minutes to think about all of these. And then afterwards, we can check back in, and hopefully some of you guys will have some thoughts, and I'll ask you to share them. Awesome.
Okay, while there's a lull, just to quickly answer a couple questions that I see in the chat so everyone can get the answers. The difference between a hash table and a hash map is that a hash table, you just put individual items in, so just like strings, and a hash map, you put in nodes that are hashed based off of the value of the key. And usually what you want to retrieve is the value associated with that key. So you basically use the hash and equals associated with the key, but then you get out the value instead. External chaining means that there's a linked list basically within each bucket, I believe. Is it possible for there to be a hash table with a hash table as an external chain? I mean, yes, physically. Will it be used? Probably not. At that point, you're most likely just going to use an array list as your as the kind of data structure within the bucket. Amortized, in case anyone's confused by that, means basically use amortized runtime when there are occasional cases where the runtime will be significantly larger, but in the vast majority of cases, it will be small. So in this case, when we resize our entire bucket system, obviously it's going to take a really long time, but in general, it's going to be really fast because we're only going to have to resize once in a very long time. So we say amortized this runtime, but it can technically take up to this runtime. I think that answers most of the things that I saw in the chat a couple times.
Awesome. Yeah, thank you, Anjali. So yeah, like why don't we move on and try to maybe answer these questions? Does anyone have any thoughts on the first question? Like if two items have the same hash code, will they be in the same bucket? Does anyone want to type in the chat or maybe unmute yourself? Yeah, so a lot of people are saying yes in the chat. That's true. So if two items have the same hash code, they will be reduced to the same index in the hash table. Perfect. So the second question was, if there are multiple items in the same bucket, how would we retrieve one of them from an externally changed hash table? Are there any ideas on how we would do that? And I've actually put an example of one bucket with an external chain. You can either type in the chat or unmute yourself. So Anisha says traverse and return when you find it. Awesome. That's a great start. Yeah, so we can basically iterate through the external chain and use the dot equals method to find the element we're looking for. Yeah, so we basically want to go to that bin. It's a linked list. So it's basically like looking through a linked list. So you want to traverse that list to find the exact element. Perfect. And so the third question that we had was, oh, okay. Well, it all appeared at the same time. So I'm not going to ask you guys the answer to this one, but it says, suppose you have a hash function that assigns words to bins based on the ASCII value of the first letter of the word. Is this a good function? Why or why not? This is actually not a good hash function because assigning buckets based on the first letter of the word has a potential for a lot of collisions, and we really want to try to minimize our collisions. So for example, if we happen to have all of the words that we're inserting starting with the letter A, all of our keys would be in the same bucket, and we would create a long chain, like a long linked list. And so let's say you want to find like the last word in that linked list, that's going to be order of n runtime, right? And we really want to try to get our runtime to be order of 1 amortized. So that's why this would potentially not be a good hash function. And also there are only 256 ASCII letters, but 4.3 billion possible integers. So that means that our hash function is not uniformly distributed across all integers. And so that's why this would essentially not be good. So Jillian asked, what is the case where the value updates to the new value? Is that when they have the same hash code and they reduce to the same index? Oh, okay, yeah. So you're asking like, is there, yeah. So that's a specific case for hash maps. So in a hash map, if you were to put if you were to put two objects with the exact same key into a hash map, then the value will update. So that's not exactly what we're talking about here, but that is true. That's specifically in the case of hash maps when we're putting in keys and then like the value is different, but the key is the same because you cannot have duplicate keys in a hash map. Awesome. So then moving on, we have a couple quick check questions for load factor. So I'm going to give you guys another 2 minutes to look at these. So why is a high load factor like 3.8, for instance? I got 3.8 because the load factor of the example I've linked at the bottom is 3.8. Why is that a problem? Consider the runtime of operations like adding and retrieving elements from a hash table. And how can we fix hash tables with a high load factor? So how would we essentially bring down our runtime? So I'll give you guys another 2 minutes for that. And yeah, as I said in the chat, like there definitely might be questions on the exam that will require you to come up with a good hash function. So I would definitely like keep in mind what makes a good hash function. Look at those slides, make sure that your function does have that uniform distribution that we're looking for and that it is efficient. And then, yeah, that was the main question I saw. So.
When you say like a good hash function, do you mean like a good hash function like after resize? So if we did it like where like it maybe at one point it has collisions, but then once you resize it, it won't.
So for the hash function, that's not specifically linked to a hash table. They're essentially, for a good hash function, that's basically assigning, like when you take an object, they want you to assign it to like a value that will not have collisions. Like when you're assigning it to like an integer, you don't want all of your hash, like all of your objects to be assigned to the integer 2, for example. Like you want that to be uniformly distributed across all integers when you're assigning. And so that's a little bit different from assigning like to the hash table, but collisions are the same for both hash functions and hash tables. Like you don't want as many collisions. Does that make sense? Or
Yeah, it does. Thank you.
awesome. Cool. And so with that, it's been 2 minutes. So does anyone have any thoughts on why a high load factor like 3.8 is a problem? Feel free to type that in the chat or even unmute yourself. Yeah, so someone said that an increased load factor means that there is an increased runtime. The runtime won't be constant. External chains are too long. These are all like, yeah, you basically don't want to have long external chains because this was essentially going to make your hash table look more like a linked list than the hash table that you want. And so that's why. And so how can we fix hash tables with a high load factor? Yeah, let's actually move to the next one. So yeah, so it is more likely that a hash table has long external chains. As we mentioned before. So for the next question, how can we fix them? Does anyone have any ideas? Awesome, resize, yeah, that is the best way to fix these, right? Increase the number of buckets, yeah, resizing. So we can add more buckets to the hash table and rehash all of the elements so that they're distributed more evenly across all of the buckets. And so this entire process is essentially what you guys are saying, we're resizing the hash table. And so that's gonna reduce your load factor and yeah, improve your runtime. Cool. And so that was hashing. I'm going to transfer it to Nikhil now, who's going to talk about heaps.
I have one more question just about the hash.
Yeah.
So I remember in lecture, Hug said something about like multiplying it by like the power, like if you for all words, if you multiply by like 27 or something like that, or like something to the power 27, it makes it so like all the words have their own bucket. Would that be something that would be like a good hash function if it was like a thing for words that they would want like a test?
To jump in, that would be a great hash function. Unfortunately, the only consequence of that is that there is a limited size to integers in Java, right? So if you remember back from like discussion 1, integers are a fixed size in Java, right? They're only what, like 8 bytes, something like that. They're very small. And what that means is that there is a max integer. It's like 2.7 billion trillion. It's a very large number, but it is finite. And so if you keep raising things to the power of 27, you're going to hit it pretty fast. So that would be a great hash function. However, it won't be as great as you would expect it to be because there will still be collisions because you'll have to come back around, if that makes sense.
Can you give an example of a good hash function?
I mean, okay, to be clear, we will never ask you, we won't be judging a question like that super intensely. And if we give you an example like that, it'll be pretty clear. I believe the question when I took the class was here is an RGB value. So like red, green, blue, here are the number values for that and create a unique hash function. And obviously 3 numbers raised to like 255 or whatever the max possible value is not going to hit that max integer. And so because of that, we could create a hash function where there were no collisions. So we won't give you something impossible if we ask you guys to make a good hash function. Don't worry, guys, we're not mean, we're not evil. Just follow these general rules. Yes, it's 2 to the 31st, apparently the maximum integer value. So just keep these rules in mind. We will make any question we give on the test physically possible, and we will give you enough information where you will be able to come up with the hash function if you remember like the rules we said. So don't stress about it too much. And even if it's there, it'll be like one problem out of like a lot of points.
Okay, thank you.
Yeah, and I think to add on to that, basically for most questions on the test we'll have, or like if there is a question, the input space will tend to be small enough such that we can create a good hash function as like the RGB example without like actually having to go beyond like the max integer. Okay, are there any other questions overall about like hashing and everything that just happened? Okay, doesn't seem like it. So hey everyone, I'm Nikhil. I will be going over the heap data structure. This will be more of a conceptual overview since we haven't covered it too much in class so far. So first, before we get into heaps, let's look at the abstract data type priority queues, in particular a min p queue. In a priority queue, each element has a priority associated with it. So one important real-life example of a priority queue is a hospital emergency room queue, where the item is the patient and the priority is the severity of the patient's condition. Basically, we want the patient with the most critical situation to be looked at first. So this would actually be a max PQ where we can add patients, get basically the current most severe patient, the person with the highest priority, so we can treat them first. And then after we're done treating them, we can remove them off the queue. So for a min PQ, we mainly want to interact with the smallest priority element. These are a list of 4 functions that we want to make functional. We want to be able to add an item to a priority queue that contains its associated priority. We want to be able to retrieve the smallest priority element. We want to be able to remove the smallest priority element. And finally, we want to get the size of the whole PQ. So before we actually get into heaps, let's look at some potential implementations for the priority queue. The first thing is if we had an ordered array representing this priority queue. Basically, getting the smallest element would just be theta 1 runtime, since it's at the very front of the array. However, adding and removing the smallest element would be theta of n runtime, as we would potentially have to shift all of the elements afterwards. Imagine if we add an element to the very start of the array, or we're removing an element to the start of the array, we would have to shift all of the elements over one spot, which would make it theta of n runtime. However, if we had a bushy binary search tree instead, we could look at all 3 functions' performance. Basically, add, get smallest, and remove smallest would all have a runtime of theta log n. And this is because in the worst case, we have to navigate to the very bottom of the tree in order to find a certain element. And this would be theta of log n since our tree is bushy. That's the maximum number of levels. So this looks pretty decent overall, but some big issues with binary search trees are that they're not inherently designed to handle duplicate values. There's some modifications we can make, but they're tricky and not like immediately apparent, especially for this class. In addition to that, we can't really guarantee bushiness as it really depends on the order that we insert elements. Like say we insert the elements 1, then 2, then 3, then 4. Basically, since each element is going to the right side, we would get a linked list and we couldn't guarantee that it was bushy. On the other hand, if we looked at a hash table, it's basically the same as working with an unsorted array, as hashing doesn't preserve priority order. So say we're hashing like a priority 1 and a priority 2, we can't guarantee that it's still in that same order after we hash it. So basically, it would be very fast to add with theta of 1 runtime. However, it'd be difficult to get smallest and remove smallest, as in the worst case, we still have to iterate through all the elements in the hash table. So basically, since we've gone over these 3 potential data structures and their trade-offs, that's where we get into heaps. A binary min heap is a binary tree that has 2 properties, completeness and the min heap property. Completeness means that the tree is only missing items at the bottom level if it isn't full and all nodes are as far left as possible. So basically, you go to the tree in order, you do like an in order traversal. Here you see that there's like 1, 4, 2, 8, 5, 3. You'll find that all of the levels are full except for the last level. And in this last level, all the elements are pushed to the side, to the left side. So it's still a valid, it fulfills the completeness property. The second property is the Min Heap property, which is basically that each node is less than or equal to both of its children. So in this case, for this tree, we see that 1 is less than or equal to 4 and less than or equal to 2. 4 is less than or equal to 8, as well as being less than or equal to 5. Same for 2 and 3. So these are the main properties of like a binary min heap. There's also a binary max heap, which is the exact same, except we have a max heap property. Each node has to be greater than or equal to both of its children elements. So coding wise, it's like the exact same implementation, but all the less than or equal to signs become greater than or equal to signs. Yeah, so based on everything we went over just now, which of the following 4 examples do you think are valid max heaps? And if not, like, why do you think so? I guess just really quickly, put in the chat the like numbers of all the valid max heaps. We can start with like 1, 2, 3, and 4 from left to right. Got it, very cool. Okay, so it looks like we have a lot of answers. It seems like everyone is saying 1 and 4 right now. Yeah, so let's take a quick look. So 1 has 3, 3, and 3. Does it fulfill the completeness property? Yes, all the levels are full. The one that isn't is like at the bottom and pushed to the left. And all of the elements are greater than or equal to all of the elements below it. The second one is 3, then 2, then 1. The property that it doesn't fulfill is the completeness property, because you see that 3 does not have a right child. Therefore, it's not a valid max heap. The third item in like here does not actually fulfill the max heap property because 5 is greater than 4. However, it's not greater than or equal to 8. So this doesn't hold. And the last element, the last tree or the last heap is just a 1. So it holds, all the properties hold. And basically everyone in the chat got it correct. So it looks like we understand that and we can move on from here. So heap operations. Now, how do we actually implement this heap to work with our priority queue from before? Basically, get smallest is easy. We just return the element in the root node. When we're adding an element to our heap, I'll explain it this way, and then I'll go through a couple examples that make it a little clearer afterwards. When we're adding an element to our heap, we basically put our new employee, which is our new item, in the very last position, and then swap upwards if necessary. I think in lecture, this is called swimming up. The remove smallest function, it was described as basically assassinating the president, which is the current root. We remove that element, then we promote the bottom rightmost person to the top to replace them. After that, we demote them by replacing them with the best successor. If there are any tie breaks, we do that. This is called swimming down, I think, in lecture. And the reasoning for all of this is we want to ensure that whenever we're removing an element in the min PQ or max PQ, the next smallest element is still at the top of like the PQ and it's ready to go. So we want to ensure that even when we're adding and when we're removing, we maintain the properties that we saw before. So I can go over a couple of examples to make this easier to understand. Basically, we have this big min PQ. There are duplicates because that's allowed. We're going to add 3. Before we go, we can see how just getting the smallest element from a min PQ is very simple. It's just getting the element at the root. Because of the properties, it must be less than or equal to everything below it. So when we're adding 3, we start by just putting it on the bottom rightmost side, the like last element in the priority queue. From there, as we saw before, we kind of just swim up. We swap every time it's valid until we can't keep going anymore. So basically we have that 3 is less than 8, so it should be above it. So we just switch the 2. We have that 3 is less than 6, which is above it. So we just switch the 2. We compare 3 and 2, and we see that 3 is where it's supposed to be, and we're done adding. So that's basically how we go over just like adding elements to the min PQ. For deleting the minimum element, this one's a little bit trickier. Basically, as we saw before, we start by taking the minimum element, which is the root, and we called it assassinating it, just removing it from the PQ is enough. From there, we then take like the bottom rightmost element, which is the 8 right now, and we put that at the root. And in order to preserve the min PQ property, we swim down this 8 until it's at its like rightful position in the company. So we basically look at its children, we see 2 and we see 3, and we think which one should be at the top. Because 2 is smaller, it should actually be there. Since this is a min PQ, that's how we're tie breaking. We want the most like valid successor to be at the top. So we swap 8 and 2. From there, we look at 3 and 4. We know that 3 deserves to be higher up because it's smaller. So we swap the 8 and 3. And then from there, we look at the 8 and 5 and 6. And we know that 5 deserves to be there more than 6. And now that we're at the bottom, we're just done. Oops. Yeah, so that's how we go about deleting min, delete min and adding elements to the min priority queue. Before we continue, does anyone have an idea of what the runtime for the delete min function would be? In terms of the number of elements, which is like n. If you do, just, yeah. Got it. So it seems like everyone's saying theta of log n. That's correct because after we promote, we just go down and the maximum number of levels in this tree, since it's like bushy, it's complete, it's log n, correct? And does anyone have an idea of what the runtime of? So Edison asked, there's no priority between the left and right children. So the thing is, when we're deleting min, there's no priority. So first we look at which one is the most valid successor. So in this case, you see that 8 has a left child of 3 and a right child of 4. So 3 is more valid, so it goes up. Oh. Yeah, so 3 is more valid, so it goes up because it's smaller. However, if we're in the case where 8 happens to have like a 3 as its left child and a 3 as its right child, if they're the same element, we'll tell you on the test or in general which way to tie break, because if they're same element, we'll tell you we always like choose the left node. So there's no priority between the left and right children if they are not equal. However, if they are equal, we will tell you which one to choose. Isn't saying theta log n, assuming that the node will always go down to the very last level. See, I guess technically it is like a big O of log n. That's like the worst case situation. But usually when we talk about like data structures in general, we define it as like even like the average case in this case would be based on like the number of elements. So it would still be like theta of log n. It's just like a little bit of a semantics thing, but I think it still holds. For adding, do we have an idea of what the runtime of the add function would be? Okay, it doesn't seem like anyone say anything in the chat, but okay, very cool. Yeah. So basically theta of log n. I guess like for like data structures, it's a little different than like doing like the runtimes of like certain functions, but it's like a semantics thing, but it is both like theta and O of log n, I guess. You can refer to it as either. I don't think it'll matter really for the test. So I think we're good here. Yeah, and it is log n because it's the exact same situation. Basically, in like the worst case, we go all the way to the top, which is log n levels. So that's all of that. And then moving on from that, do we have any questions about any of the functions that I just described? If you do, feel free to unmute and ask anything.
What is the time for add again? I missed it.
Yeah, so adding is here. It also happens to be theta of log n because when we're adding an element, at its best, we can swim up log n levels. Or like in the worst case, we kind of do log n swaps since that's the number of levels. So it's like a very similar reasoning to why delete min was theta of log n.
Makes sense. Thank you.
Yep, of course. Any other questions? Got it. Okay, I'll move on then. So this is a really important concept. How do we actually represent a tree in Java? So how does like Java represent a tree? One idea we went over in class, the very first approach was basically creating a mapping from each node to their children. The problem with this is this just like wastes a lot of space creating like this structure each time, deleting it. There's a lot of complexity there. The second approach we went over was actually storing the keys in one arrays and the parent IDs in another array. So that's a pretty solid approach here. You can see we have this keys array with everything in order, 1, 3, 5, 4. We have all the parents, so 0 is just 0. 1 is like the 3 nodes parent is like the 0 index. The 2 nodes parent of 5 is a 0 index, and the third node's parent is a 1 index. So that's another way to basically represent a tree in Java, but there's a way to do it more efficiently. And that's basically just storing the keys in one array and having no other structure. So as you can see for this case, we kind of just go through it in order. We have the first element be the 1, since that's the root. The next one is the 3. The one after it is a 5. And the last one is a 4. So if the tree is complete, we can just store the keys in one array, and we don't need to have another array saying what you're like the parent of. My question is, why does this work for a complete tree and not like another tree? Just having one representation for the keys. And not having, as we saw before, basically another array for parents. What is K? So I think I'll go over that in a second. But K is basically the index that you're in. So I'll go over that when we get to it. Yeah, so why do you think like just having one array for the keys and not having another array for the parents would work for like a complete tree and not for another tree? Yeah, so Anisha said for incomplete trees, the levels would be off. Yeah, so that's exactly it. Basically for a complete tree, we already know what the parents are. Yep, exactly. We know where every single element should be in a complete tree, and we know that things aren't missing. So as you see, like we know that like the 1 should be here, there's a 3, there's a 5. So we can just represent everything in order, and there's no like, basically if something was missing on the other hand, we wouldn't know if we had like 1, 3, 4 and that 5 node wasn't missing, we wouldn't know whether the structure would be referring to just like a 3 node tree with like 1, 3, and 4 on the right side, or like a linked list type thing with a 1 and then its left child is a 3 and the left child is the 4. So like we're missing a lot of information there. However, if the tree is complete, we know everything should be in the position that it's in, and we don't need to have a separate array to have the parents. And I think Jesse also asked a question. So yeah, so these arrays, these approaches here would basically apply for only complete trees like the heap that we just mentioned. So for a complete tree, we can basically do these calculations since we know where all these positions are. We start with the root as the first element, so it's at the 0 index for approach 3a. The second element's at the 1, then 2, then 3, everything's in order. And we have some equations to basically, given that we're at a certain element with an index k, calculate our parents and our children's location. So say we are at some k, our children, or like the node's children, are 2k plus 1 and 2k plus 2. So in this example, say we're at the root, which is at the 0 index. The left child would be 2 times 0 plus 1, which is the 1 index. As we can see, that's correct. That's where like the 3 element is. The right child is 2 times 0 plus 2, the second index. So as you can see, that's correct. That's where the 5 is. On the other hand, if we go to like where 3 is, that's the like first element, and that's what k is. So its left child should be at 2 times 1 plus 1, which is the third position, and that's like correct based on the array. And it also works the other way, where given that we're at some like child, we can also find its parent. So as you can see here, the parent of 3, which is at the first index, is k is equal to 1 minus 1 divided by 2. That's just 0. So as you can see, the parent 1 is at the 0 index. If we go to 5 and we do the same computation, we do 2 minus 1 over 2. And the gist is that we actually like round down in this case. So it's still the 0th element and it's 1. Someone asked, for the add method of a heap, will the runtime not be theta of n, O of n, since finding the last position tree will take O of n? So if you look at like this type of structure for storing a heap, finding the last element in a tree is not going to be O of n because like we literally know where the last element is already. So we don't actually need to go and find it. Yeah. So that doesn't actually really contribute too much to the runtime. So does everyone see how, given like this approach, we can actually find out, given we're at some like node, we can find where its like children are and where its parents are. There's also another approach, which is literally the exact same thing, but we leave the 0th element of the array empty, and that just makes it like slightly easier computation. Instead of like the k minus 1 over 2, we just do k over 2. Instead of like the 2k plus 1, 2k plus 2, we have 2k and 2k plus 1. Does anyone have any questions about how we represent this tree? I think this was like the final implementation as you saw in class. And if there's any like distinction between like whether we have something at the 0th element or not, I think they'll tell you on the test. Just to check. Jesse, if you want to paste your question to the whole class so everyone can see it. Got it. So just to check, approach 2 with 2 arrays would still work for all other trees. Right, on the exam even it's not. Yeah, so basically I think on the exam we'll mostly be looking at an array representation as in approach 3 for complete trees like the heap. As you said, you're correct. This approach 2 is a lot better when even if the tree is not complete, it'll still work. So exactly what you said. I don't think there'll be many situations where you will be doing this for a non-complete tree. If the exam mentions a heap, do we always assume it's a binary heap? Yeah, I think that's a pretty fair assumption to make. And I think for the most part, it'll actually specify that it's a binary heap. We haven't talked about anything else in this class. Why choose this over a node style tree? Yeah, exactly what Anjali said. They probably won't ask you to use an array representation for a non-heap tree, so it'll always be this singular array approach. Yeah, so the get smallest runtime, Ishan, I'll go over in the next slide actually. But basically the get smallest is, oh, it says O of log 1. That should be just O of 1. But it's just O of 1 because it's literally, we're not removing anything, we're just looking at the root. Yeah, so this should be O of 1. We'll correct that later. And are there any other questions? Marco said, yeah, why choose this over a node style tree? So the biggest thing is this is just so much easier to represent. Like instead of having like this tree structure, having to specify its children, have like a recursive data structure, and have like all of that storage, where we literally need to like iterate through every element in order to like get to 4. In this case, like everything is just so clean in like this array. And when we want to get to its child, we don't even need to like go into another like node. All we need to do is like just do this like very simple like mathematical computation of just like multiplying by 2, adding 1 in order to get to like its child. So the main gist is that this is just like a much simpler, more like concise way of representing a tree, as opposed to actually storing all the nodes and everything, because just space wise and it's just not very efficient. Does that answer your question? I think Marcos, you asked that. Got it. Very cool.
I was wondering if you go over approach 1 and 2 again. I was kind of confused on how those worked. Like, if the parent isn't the second element's parent going to be 1, not 0?
Yeah, you're right. So the second element's parent is like the number 1, but we're actually treating these as indices. So the second element's parent is at index 0. Do you see in the
That makes sense. And then just one more question in regards to trees. Do we don't add to trees like we do like the how do I say it, left-leaning trees, like left-leaning red-black trees.
Mm-hmm.
Not red-black. There's like some type of tree we wouldn't add the same way as a min heap. The min heap is like is the only one where you add it and then you switch it and then you bring it back up.
Yeah, so like, yeah, the Min Heap property, the reason we do this is because we want to like maintain that min heap structure. It's not the same as like a typical binary search tree where we like can index into the right element and just like add it there. This is special because like every time we add, we want to make sure that like those properties, like the min heap property and the completeness property are both like fulfilled.
Makes sense. Thank you.
Yeah. Do we have any other questions?
Yeah, sorry, I'm a little confused. Why can't we index into, or what allows us to index through a binary but not a heap?
What do you mean by that exactly?
So I'm sorry, I don't know if I caught it correctly, but you said you can't index in, like a binary in a heap.
You can't index into a binary and heap. I don't think I'm properly understanding.
I think
Yeah.
what she's asking is that, well, I think this is at least what my interpretation of this is, that you can't exactly just, basically for a heap
Oh, I
structure,
see.
only the top node is guaranteed to be anything, right? And so in a binary search tree, for instance, you know that like the smallest node will be in this location, the biggest node will be in this location, and like the third smallest node will be in this location. Like the binary search tree, every node is in a very specific place dependent on its place in the tree. In a heap structure, all we really know is that the top node is the minimum and that every node below it is bigger than it, and that kind of carries on. But indexing into a heap does not give us very much information. And if you want to find a specific value or something, you can't really index into a specific point in the heap to find it, right? Like if I want to find 11 in this heap, I wouldn't know where to go because obviously 11 is going to be below 2, but it's also going to be below both of the 3s, and it's going to be below the 5, 4, 6, and 7. So it could be anywhere in this entire heap. So a heap isn't really used when you want to see a whole bunch of, when you want to like be able to access a whole bunch of different data. It's mostly used when you just want to have like a queue, like basically only one thing coming out at a time, and that thing is either the largest or the smallest in your set. Does that make sense?
Gotcha. Yes, thank you so much.
Yep, that was a really, really good explanation. And then yeah, so this is the table with like the heaps runtimes added to it. This says log of 1. It should be data of 1. But basically add happens, as you guys said, in theta of log n. Remove smallest happens in theta of log n, and getting smallest is just viewing the root. So that happens in theta of 1 runtime. As you can see, that's like better than everything that we've seen so far. And in addition to that, it is fine with handling duplicates. We don't need to worry about that. And we guarantee, based on the operations we do each time, that the tree is always like complete and it satisfies our either min heap or max heap property. Yeah, so does anyone have any questions at all about what just happened? How do we know if a node doesn't have any children? Yeah, so you're saying in approach 3, if we're at some node, okay, I see. So basically we know the length of an array, right? And if we do this like 2k plus 1 or 2k plus 2, and that happens to be like greater than or equal to the length of the array, we know that it's not possible to be in this array. Like, since we know that this array is like 4, if we look at like 3, for example, and we do like 3 times 2 plus 1 is 7. 7 is like greater than the length of the array, so there's no way that it can be here, which means that it just doesn't have a child. So basically, if like it's out of bounds, if our left child or right child that we compute is out of bounds of the array, we know that it just doesn't have that child. Yeah. Any other questions?
And how do you know if it's out of bound or not out of bound?
Yeah, so one thing we can do is actually just compute the length of the array. So since this is an array, right, we just like, I think we have like the size function. So we know the number of elements, and like if, so here the size is 4, right? So if the left child or right child we compute is greater than or equal to 4, it'll always not be in this array because we know that there's no 4 index, right? So It's basically just the like actual length of the array, and Java has a function to like do that for you.
Okay, thank you.
Yep.
Great. So if there are any final questions, we can take them now. Otherwise, we can wrap this up for today and give you guys some time to work on homework 2 and study for the midterm on your own. So if you guys have any questions, ask now or hold your peace. And of course, you can always ask on Ed and stuff after, and we will be answering questions promptly for the next couple days up until the midterm.
Yeah, just to make sure I understand it correctly. So if we want to like represent a not complete tree in arrays, then the length of the array will actually be will be larger than the number of elements in the tree. Is that correct?
Yes, that's correct, right? Because if you are trying to represent a not complete tree, then obviously there will be some spots within your representation where there is no actual item. And so you will need more spots than there are possibly items in your tree structure. I think I see some questions in the chat. Could we go over quick union and weighted quick union heights again real quick? You can find this also on the slides from lecture, but I'll go over them real quick. So for quick union, when you're combining two sets, you don't care how big they are, you just combine them indiscriminately, which means imagine you are combining a set of size 3 and a set of size 1, and you don't care which way you combine them, so you attach the set of size 3 underneath the set of size 1. So now you have a set of height 4, and you keep doing that over and over again, right? And because you can do that, the max possible height for quick union is the number of edges, or the number of nodes minus 1. Weighted quick union, on the other hand, enforces that you can only ever have something that is at most log the height of the number of nodes. And the reason for that is if we again take our example of something of height 3 and something of height 1, weighted quick union will enforce that we will attach that item of height 1 to the item of height 3. So we won't have that issue anymore. If you're still not sure why that's the case, I recommend you look at lecture or try to draw out some trees and try to prove why you physically cannot end up with a tree larger than log n. So try drawing an example of maybe up to size 8, maybe 16 if you're still not sure, and you will prove it to yourself that it's physically not possible. Why isn't the runtime of add theta n? For which data structure are you talking about? Is it heaps, Evan?
Nikhil answered it. So
Okay.
Thank you.
So for heaps, I'll just say it out loud because I don't think the chat is in the recording. But the reason it's not theta n for resizing every time when you add, it's because of array lists. Another reason is just because if we use the type of resizing that we did when we did the double-ended queue, if we multiply, right, we're only going to have to resize once every very long time. So we can say amortize that it does not take n, it takes 1. Okay, so again, any final questions or can I end this now? Okay, for weighted quick union, how do you find the best case height if you are given a specific number n? So it is log n, it is specifically log 2n, but you don't ever have to do log 2n when we're talking about, or I guess, yeah, it's log 2n. You might have to do specifically log 2n. Again, I recommend you draw it out and you will see this pattern that will take place. I believe there's a discussion videos that cover it either from this semester or from last semester where we kind of draw out all the different cases on how you can combine sets of different sizes and how the height changes depending on what set you combine. Okay, so I am going to stop recording.